Hi, I'm Sivian. I'm your today tutor. Let's review. What is today's tutoring question? What do we need to control in the product to be sterile filter? What do we need to control in the product being sterile filter? There are 6 points that we need to focus on. 1. Microload. 2. Total solid loading. 3. Product viscosity. 4. Flow rate. 5. Pressure. And 6. Filterability. Now, let's review from the point of microbe load. We want sterile filter to be able to remove all microbes in the product. Thus, it is important to use an absolute rated filter to prevent the carryover of spoilage organism into the pack. As the filter needs to be cleaned periodically, attention is required to the water cleaning system as the debris inside will prematurely block the sterile filter if the pre-filter of water cleaning system is not correctly sized. Some companies allow a certain amount of microbe in the product, example, 1 colony forming unit per milliliter. Thus, it is important to understand the tolerable microbe in the pack first. As I highlighted earlier, we want sterile filter to be able to remove all microbe in the product in order not to have any infected product in the packaging line. Next, let's continue review from the point of product viscosity and total solid loading. A cloudy product must have cloudiness removed prior to sterile filter. If not, the solid content will block the filter after a short period, giving low filtration throughput and high pressure drop across the filter. Sterile filter is particularly sensitive. Once blocked by the solid content, it may be permanently damaged. Primary filtration, like depth filter, is usually used in the upstream process. Take note, sterile filter should be used to ensure no microbe get into the pack. It is not to clarify the product. Next, let's review the point of flow rate. High flow rate equal to high differential pressure across the filter. High flow rate and high differential pressure are closely related in filtration processes. When the flow rate increases, the speed of the molecule also increases. This higher speed means that when molecules collide with the membrane, they have a greater chance of sticking to it. This point is important in filtration process as it can prematurely block the sterile filter, hence affecting the efficiency and effectiveness of the sterile filter. It is better to run a large filter at lower flow rate than forcing the product through an undersized filter to achieve high flow rate. We should follow the manufacturer recommended flow rate of the filter. So, what type of filtration is suitable for higher flow rate? It is cross-flow filtration, which is used in CIP. Higher flow rate can clean off folding more effectively. Next, let's review from the point of pressure. Differential pressure across the filter will increase once the filter getting blocked. Subsequently, it will making the filter feel stretched. This pressure shock is likely to damage the filter. As we know, filters have pores. If we try to push a big size of product through the pore, by force, what happens to the pore? It will open up and become enlarged. Subsequently, it is no longer retain the microbe effectively. If this case happens, then your filtration job will become wasted. How do we check the pore size is adequate to detain the target particles? We can perform the microbe analysis on the product to ensure the results are meeting the specification. Do remember to run the filter at specified differential pressure. Next, let's review from the point of filterability. Some problematic substances are sticky to the sterile filter. These substances increase the product viscosity and reduce filtration flow. Do you know which substances are categorized as problematic substances? They are glucans, pentosanes, proteins, and pectins. Testing method like base hydrolysis method, substitution method, HPLC method can be used to check the content level of these substances. Subsequently, we will be able to know how filterable the product is. We can add enzyme to the product in order to remove these substances. Example, enzyme glucanase can be used to remove glucans. Enzyme protease can be used to remove protein. We can also adjust brewing process to remove these substances. Example, we can use well-modified malt, which is having lower glucan content. Once we manage to remove these problematic substances, then the performance of the sterile filter can be sustained. This slide is talking about Darcy law. Q equal to K times dP times A divided by mu and L. Q refer to flow rate, K refer to filter material permeability, A refer to filtration area, mu refer to product viscosity, L refer to bed depth. Darcy law is fundamental in understanding and optimizing filtration process. In our case, the filtration process refers to sterile filter. Darcy law describes the flow of a fluid through a porous medium. In our case, the porous medium refers to sterile filter. So, let's review back this Darcy law again. The flow rate Q is directly proportional to the filter bed permeability K, differential pressure dP, and filtration area A. The flow rate Q is inversely proportional to product viscosity mu and bed depth L. By applying Darcy law, we can design and optimize the sterile filter system to achieve desired performance and efficiency. That's all for this tutorial section. Thank you all.